Here is a little lecture for you on LeChatlier's principle that you can use with them or whatever you see fit. LeChatlier's principle is a classic equilibrium move. We can look at the word in French and understand sort of the parts of the word and what it means. Le in French means if you have a system at equilibrium, le, lying at equilibrium, it is at equilibrium. And then chat means, oh, it is disrupted. Oh, no. And then lier means it will move forward or backward to minimize the disruption. See, that's what the French origin of the word LeChatlier means. Chatlier's principle. Let's write this down. If you have a system at equilibrium and it is disrupted, it will move to minimize the disruption. That is what we need to know. The title of this unit is LeChatlier's principle. All right, now that we've paused me and given you a chance to write that down, let's move on in life. Here's an example. Little pig, he's at equilibrium. Uh-oh, the wolf blows the straw house down, and then he has to move. He has to go, in this case, forward. Oh, we're not on pen. Oh, now we're on pen. Now he has to move forward to get back to his brother's house of bricks where he can be, at equilibrium again. Was at equilibrium, disrupted, moved. LeChatlier's principle, right there. Class over. Hope you enjoyed it. Just kidding. Okay, so there are ways to mess with the reaction, so ways to disrupt its equilibrium. It previously had some balance. Oh, that's not what we wanted to do. It previously had some balance of products over reactants. It was some reaction where reactants were turning into products and products were turning into reactants. Both those things were happening, chugging along, and it was at some balance of these things that made our K. Big, small, whatever. Okay? If we add more reactant, okay, if you put more reactant there, that means there's going to be more of these R's, okay, a bunch more R's. Which reaction is that going to increase? That is going to increase the forward reaction. The forward reaction happens when these reactant R molecules bump into each other. There's going to be more of those collisions, so there's going to be more of those forward. So if you add more reactant, the reaction is going to go forward. Okay? That should make some sense. It is minimizing the new extra reactant. It is taking that away and using it up in going forward. If, on the other hand, we were to remove reactant, okay, if we're to have less of this stuff around, oh my gosh, there's not even any reactant. Oh no, now what reaction is not happening? You're not going to see any forward reaction happening. And so all you're going to see is reverse reaction. And so if you remove the reactant, all was an extreme case, if you remove some of the reactant, there's less of those forward reaction happenings, and the backward reaction becomes dominant. I'll draw a little forward reaction. Oh, there's a little bit. And a little R. Okay, so there's a little bit of it happening, but there's more reverse reaction happening, so there's a net drift backwards. It should be pretty easy for you to fill in these other two squares. If you add more product, it's going to go backwards. If you remove product, if there's not product molecules around to go backwards, then the forward reaction dominates, and that's the way it goes. Smile and nod, discuss the people around you. Bloop. Heat. The other way you can disrupt, or one of the other ways you can disrupt a system that's at equilibrium, is by changing the temperature. Okay? How the reaction is going to respond depends on whether it is endothermic or exothermic. Breathe in. Activate that part of your brain. Endothermic. What did that mean vis-a-vis heat? Okay. If it is endothermic, heat is a blank. Or if it's exothermic, heat is a blank. Fill that in. Think. Use brain. Okay. So if it is endothermic, heat is coming into the reaction. Heat is a reactant. Okay. If it is exothermic, it is something that exudes heat. Heat is a product. Okay. So you can then use these and the rules we just developed to think about how this reaction is going to go. If you increase the temperature, you're adding more heat. If heat is a reactant, that's something that's going to drive the reaction forwards. If, on the other hand, heat is a product, it's a reaction that puts heat out into the surroundings and there's already heat there, that's the weird situation where heating it up is going to make the reaction go backwards. Okay? We generally think that heat propels reactions forwards, but if the reaction itself is exothermic, that is not the case. It is not favored at higher temperatures. In fact, it does better at lower temperatures. Okay? The other part of this is then going to be pretty apparent. If you take the temperature down for an endothermic reaction, that's going to make it inclined to go backwards. For an exothermic reaction, that's going to make it more likely to go forwards. Pause if you need to discuss with the person next to you. Bloop. Okay, changing the pressure. We generally imagine this with some sort of cylinder where we have the reaction, it's at some sort of equilibrium. We could have some K sub P for the gases. Okay, they're changing, products turning into reactants, reactants turning into products. And then we could increase the pressure. We could move the piston down and give them a smaller space to work with. Okay, increase the pressure, often by decreasing the volume. That would be if it was an increase. I'll just say that it is here. Increase the pressure by decreasing the volume. We move this guy over a little bit. Okay. That male thing is going to be so annoying, but I'm just going to ignore it. Hope it goes away. Okay, so if we have this situation, 2 A molecules and 3 molecules make 4 C molecules, and we say, oh, we've increased the pressure, what is it going to do in this case? The trick here is to notice that this stuff is solid. How much space do solids take up relative to gases? The answer is not very much. Okay? A gas particle is flying around that takes up a lot more space. If you liquefy some gas, it ends up as a little puddle. If you freeze it even further, most things besides water are going to get even smaller. Okay? So a gas would take up a lot of space. A solid doesn't take up much. If you decrease the volume, it's going to go to that side that takes up the least space. Okay, if you increase the pressure by decreasing the volume, it's going to move to side with less gas because that is a smaller volume. So in this case, if we were to increase the pressure by decreasing the volume, that would cause the reaction to drift forward. You get more of the solid made and less of these gas particles. It's easy to kind of think about it if you think about like where are the reactions happening? Is a reaction going to happen? If you're in this situation, it's rare for these gas molecules to strike each other. They can get kind of lost in this big old empty cylinder. If they're in tight, okay, they are much more likely to find each other. You're much more likely to get a collision between 2 gas particles and thus a reaction. So in a small space, things that have numerous gas particles are likely to collide with each other more. More collisions means they're more likely to have a reaction. Same situation, increasing the pressure by decreasing the volume. I'll get out of this yellow that's hard to read. Here we have 2 gas particles plus 3 gas particles making 4 gas particles. It's all gas. And now we look at the total number of particles. On this side, you have 5 gas particles. On this side, you have 4 gas particles. Okay? So the same rule applies that we had before. This side takes up a little bit more space. It is 125% bigger if you're over on this side compared to if you're on the product side. So once again, if you gave this a small space, that would make it move towards that denser form. Right? If there's less total space available, if you increase the pressure, the system's going to move to minimize that disruption you just did. The disruption you just did was squeezing it. It's going to move into a more compact space where that's not going to be as much of a problem. Hopefully that makes some sense. The other way that you can increase the pressure is by adding an inert gas. What is an example of an inert gas, my friends? What's that you say? Helium. Helium, not me. Okay? Helium, indeed, is an inert gas. Neon, xenon, all sorts of noble gases. In many cases, nitrogen is also an inert, stable, non-reactive gas. Also, if it's adding something that's not in the reaction and doesn't react with something else in the reaction, doesn't like bind to the product, doesn't increase the amount of reactant. Okay, if you add something that's not in the reaction, this is going to cause the forward reaction to keep happening and the reverse reaction to keep happening. And so it's going to have no effecto, as they say in French. Maybe. I don't know. So this will not have an effect on the equilibrium if you add inert gas. The amount of space that the gas particles themselves take up is negligible. So if you add another gas particle here, these are all gross exaggerations of their size. There's just as much room for these things to bounce around, even with like 10 moles of gas in there. We generally assume that it's going to have no real effect, and so therefore adding inert gas, no effect. The last possible way we can mess with something is to add a catalyst. You should hopefully now, by this point, know what a catalyst does. It lowers the activation energy from that to that. It does not change the level of energy of the products or reactants. It affects the speed. It makes things speed up by lowering the activation energy, but no effect on these sides of things. Catalysts affect the pathway in here, but they don't affect either end out here. They don't affect the relative energy level of your products or reactants. And so therefore adding a catalyst is also not going to affect equilibrium. Okay. It may get you to equilibrium faster, but the equilibrium position you're going for is not going to change. Here is Henry LeChatlier while at equilibrium thinking. All right, now here's some sample problems. Let's write this stuff down. If you have a reaction that has a delta H of 345 kilojoules, that is a positive delta H. That means the reaction is what? Gaining or losing energy. Think, my friends. Okay. If we say that it is a positive delta H from the reaction's perspective, it is gaining energy. Like when carbon dioxide goes through photosynthesis and turns into sugar, that is a more energetic molecule than what it was before. Okay? In this case, the reaction is endothermic. It absorbs heat. Heat is a reactant in this reaction. So adding more heat is going to make this reaction go, what do you think? Forward or backwards. Okay, more sunlight makes photosynthesis go forward. More heat makes it happen better. Okay, so a endothermic reaction absorbs heat, goes forward if you add heat. All right, here on the other hand is one thing with a negative delta H. This reaction is going to be exothermic. Heat is a product. Adding heat will make the reaction go backwards. Smile and nod. All right, let's look at a fuller problem. Write down this scenario that I just covered up and made hard for you to write down. Okay, write down this reaction. 3 hydrogen plus 2 nitrogen make 2 ammonia. This is not to say it has a delta H of 450, but that heat is on the product side. Slightly different way of thinking about it. You can handle it. This reaction, every time it happens, produces 450 kilojoules of energy. Let's mess with it. Let's knock it out of equilibrium. First thing we're going to do is we're going to add nitrogen. If we add nitrogen, nitrogen here is a product. Okay, I'll let you think about that. And we'll also remove hydrogen. All right, how is it going to respond to these two stimuli? If we add nitrogen, that should make the reaction go forward more. If we remove hydrogen molecules, if there's not hydrogen molecules colliding with nitrogen molecules anymore, the forward reaction is going to be minimized, and the reverse reaction continues unabated, and so therefore you're going to see the reaction drift backwards to create more hydrogen. If we decrease the volume of this container, oh, now I have to think about this gas stuff again. This side over here has 4 gas molecules. This side over here has 2 gas molecules.
Papa.
Yeah.
Where's Mama?
In the sunroom, I think. So if you decrease the volume of this container, if you make it squeeze down, it's going to want to go to the side that takes up less space. Which side is that? This side takes up less space. It has less gas particles. So I guess we have instructions on this written down over here. We'll go get those. All right. So decrease the volume, increases the pressure. It's going to move to the side that takes up less space, and that is the forward side in this case. All right, here's some more ways we can mess with this reaction. We could cool the flask. We could make this thing colder. Okay? If we take heat away by cooling, it's going to want to replace that lost heat. Which way will it move to replace the lost heat? It will move forward. Okay, I have some notes over here. This is an exothermic reaction. Heat is a product. Because heat is a product, we know it's exothermic. So removing heat will cause it to go forward. Adding helium gas will cause it to go backward and forward and have no net effect. Because helium is not in this reaction, and none of these things are going to react with helium. Okay, here is France at equilibrium. Uh-oh, here comes Germany invading. We have to have reverse reaction happening and push them back. And then it got back to how it was again. Another example of LeChatlier's principle in France. All right, here's an AP exam question on this topic. Actually, you know what? I'm going to jump to this one first. All right, here's a reaction. In a sealed rigid vessel containing only barium oxide solid in equilibrium with these things. So we've got a container and it's got like this stuff in it. Oh, I got to draw. Okay, container sealed. Okay, and it's got all 3 things and it's represented by the equilibrium above. Which of the following changes will increase the amount of Ba2S in the vessel? So that is asking which thing is going to cause the reaction to go forward or backward? Backwards. Okay. So they're saying what change would cause the reaction to go backwards? Removing O2. If we remove product, is that making the reaction go backwards? No. Removing a small amount of the other product, is that going to make the reaction go backwards? No. Okay, because those were the products. Adding helium, come on, we just did helium, you clowns. It doesn't change the position. Lowering the temperature. It's a good chance it's going to be it because we've ruled out the other ones. Let's just check. The delta H is positive. That means this reaction absorbs heat. So that means that if you gave it more heat, that would cause it to go forward. Lowering the temperature is going to cause it to go backwards. Okay, backwards is going to fill in the heat. So this, I made it D. We had to think all the way down on that bottom problem, is the right answer. Okay. Now let's do a free response question on this sort of situation. Once again, we have a solid as our reactant. Not going to take very much space. Hint, hint. And we have two gases as our product. We have a delta H that is positive. 93 is the number. Whatever. Okay, so one thing that's worth noting here, we place some solid stuff in a container. At equilibrium, some of that solid remains in the container. They haven't used it all the way up yet. It still remains in the container. Now, let's predict what's going to happen with each one of these ways that we could mess with it. Number one, the effect on the equilibrium partial pressure of ammonia gas when additional solid is introduced in the container. Think about that. Write down an arrow, either forward, backward, or no effect. Feel free to talk to your person next to you. B, the effect in equilibrium partial pressure when additional solid H2S is introduced into the container. So adding some of this stuff. Part C, the effect on the amount of this product when the volume of the container is decreased. Okay, if you squeeze it down, increase the pressure, what is that going to do to the mass of this stuff? And the last thing that you're going to draw an arrow to predict, you've got the letters A, B, and C, and an arrow next to them predicting what effect it's going to have. It's going to drive the reaction forward or backwards. D, the effect on that reactant when the temperature is increased. So you are writing down 4 arrows. Feel free to talk to the person next to you or pause the video, Joe, if you want to. And then we'll see the answers in 3, 2, 1. Okay, so in part A, this will be unaffected. Why? Because there was already some solid there. Solids don't appear in our equilibrium expressions, and we already had a bunch of it. So adding more extra solid doesn't change things. So this one has no effect. Forward and backwards, no difference in the equilibrium. Okay. The next one, we're adding additional H2S. Now the fact that it's solid initially makes us be like, uh-oh, is this just going to be a no effect as well? Because this is this product that normally exists as gas, I think they're meaning that this is going to then quickly sublimate and turn into a gas. And so you're adding more product. What is the effect of having more product going to be? I predict it's going to go backwards. Let's see what they say. The equilibrium pressure of the NH3 gas would decrease. In order for the equilibrium pressure constant to remain the same, to be constant, hey, it's a constant, the equilibrium pressure of NH3 must decrease when the pressure of H2S is increased. A complete explanation based on LeChatlier's principle is also acceptable. So this AP prompt saying you could do it in terms of the K sub P, or as I just did, since this is the section we're on, we can do it in terms of LeChatlier. Okay, let's see what our next one was. The effect on the amount of product when the volume of the container is decreased. Okay, this has 2 gas particles on the product side and 0 gas particles on the reactant side. If we increase the pressure, it's going to want to go to the side with less gas. In that case, this is the reactants. So my prediction is that once again, it's going to go backwards. Okay, let's see what they say. The mass of the reactant increases. A decrease in volume causes the pressure on the gas to increase. To maintain a value of the pressure of the equilibrium constant K sub P, the pressure of each gas must decrease. Again, I'm doing LeChatlier's thing here instead of what they've got there. All right, the last one. Okay, the amount of solid when the temperature is increased. So we're doing increase the temp. Increase heat. This is a endothermic reaction. It absorbs heat. The chemicals gain heat in the course of the reaction. So putting more heat in is going to drive the reaction forward. Okay. I wonder if it's going to be, let's just look and see. The mass of this decreases because the endothermic axis rotates heat. It goes near to completion, more to the right as the temperature increases. Phew. I was worried there was going to play some trick with like the solid didn't matter. But the reaction keeps happening, and that decreases our amount of solid, drives the reaction forward. So this is going to be forward. So our arrows were tricky back and forth, backwards, backwards, forward. Hope you've enjoyed this lesson. I hope you learned something along the way. Have a good